Okay, so today's class, let's start now. We have made an appointment at 10 o'clock in the morning, but apparently you all misunderstood it to be 10:30. Uh, how do I turn off the caption? All right. So today's lecture number 13, and there's gonna be a couple more lectures before we take the midterm. The midterms on next Monday, which is 26th of February. Um, right. So, reminder. The midterm is coming up on Monday, which is not this Monday, but the next Monday, the following Monday. The date is 26th day of February, and I believe the time is 1 p.m. to 4 p.m. All right, please confirm the time again. Okay, so last time, what did we talk about? We talked about convolution integral. So we have a system, an LTI system. And LTI system. This system has an impulse response of h of t, and we apply the input signal x of t into this system, and we measure the output signal, which is called the response of the signal, and the response is denoted by the symbol y of t. So for when all the initial conditions of the system is set to 0, meaning that the system doesn't have any initial states, the output y we will call the zero state response. And for this, we denote it by y of zs. Zs stands for zero state, and actually we can find the zero state response from the LTI system using this equation. YZS can be found by doing convolution integral between the impulse response of the system and the input signal. And the convolution integral is defined by the integration going from minus infinity to infinity h of tau x of t minus tau d tau. Now this is a very important integral, and you have to be able to perform it to succeed in the midterm. Okay, and we have performed a couple of examples, and we could come up with a couple of formulas. Okay, for example, if we convolve the unit step signal with itself, the result would be the unit ramp signal. Okay, and if we perform the one-sided exponential signal with the unit step signal, the result would be 1 over alpha 1 minus e to the negative alpha t u of t. And we also know that any signal x convolved with the unit impulse signal will result in the same signal back again. That's because this is because of the shifting property of the unit impulse signal. Okay, yeah. So these are a couple of examples that we have addressed. We also talked about, in the last lecture, we talked about some of the properties, some of the important properties. The first of which is the linearity. Linearity means that if we perform convolution of h of t with a linear combination between signals, okay, we could in practice take the function h inside of the parentheses and get a1 h of t convolved with x1 plus a2 h of t convolved with x2. Okay, so that was the first property, which is a very important property. The second property is commutativity. Commutativity states that we could either change the order of the convolution integral. So it doesn't matter if we bring h up front or bring x up front, the result would be the same. We could switch the order between them. The third property is called associativity. In this property, if we are doing convolution integral between three functions, okay, we could, doesn't matter whether which pair we start with, okay, we could start with any pair as long as we have as long as we perform the convolution integral between the three. So for example, if we have h1 ht, if we have h1 of t convolved with h2 of t convolved with x of t, okay, this we could put parentheses around here, meaning that will be doing convolution integral between h1 and h2 first, and then the result convoluted with x of t. Now this is going to be the same as we are doing h2 and x first, and then result convolved with h1. So it doesn't matter which pair we start convoluting, okay, as long as we do all of them, we're fine. That's called associativity. Another property is the distributivity. Distributivity, just like multiplication. So actually, the first property was not linearity, it was distributivity. Sorry, the first property was distributivity. And see, let's see. Time delay, right? Time delay. Time shift. Time shift. The next property is the time shift property that we talked about last time. The time shift property states that if we shift the input x by t0, so if y of t is the result from convolving h and x, then if we convolve h with x that is delayed by time t0, the result would be y delayed by time t0. Also, if we delay h by time t0 and convolve with x, the result would be again y delayed by time t0. So if we look at the diagrams, that this one that represents this one, okay, we have delayed by time t0, and then we put it into the linear system h of t, and this is the result. On the other hand, if we put it into a linear system h of t and we delay the result by time t0, okay, the result would be the same. Okay, these are x of t, the same x of t. So we could switch the order between h and the delay without changing the result from the convolution. Okay, so that's what it means. Now, today we're going to talk a little bit more about additional properties of convolution integrals, which will be helpful when we perform convolution integrals. Okay. Now the next property is called the derivative property. Suppose that signal y is a result from convoluting x and h together. Then if we take a first derivative of x, okay, what comes out of the differentiation, and we convolve the derivative of x with h, the result will be the same as taking the derivative of y with respect to time. Also, it is going to be the same as convolving x and the derivative of h. So this is going to be very helpful. Now, if we take a look at this using diagrams as usual, so we have x of t coming in, and we take the first derivative of it with respect to time, and we put it into a system with the impulse response h, and we record the result. Okay. On the other hand, if we put the input into the system and we differentiate it with respect to time, and we record the result again, then these two results will be the same. So again, we could switch the order of the LTI system and the derivative with respect to time without changing the outcome. Okay. Also, if we take a first derivative of both of them, both x and h, we take a derivative with respect to time, and we convolve the result from the derivatives. It follows that the result would be the same as taking the second derivative of y with respect to time. Okay, so if we denote this, says that if we denote y equal to L of xt as x of t, as h of t, h of t convolved with x of t we denote this, we use this notation to stand for the output from the system when the input is a signal x. So we know that when the system is linear, we can write this response, this output, using the convolution integral between the impulse response and the impulse signal. So this statement, this property, means that if we differentiate the input with respect to time and put it into L, the result would be the same as taking the first derivative with respect to time of Lx. So in other words, we can interchange the order between between the operator L and the derivative operator. Okay, we could interchange them. See, here I took d by dt outside of the parentheses and perform L first and then take the derivative. So this is the same. These are the same. Okay, now this will come in very helpful. For example, here, let L be an LTI system where the zero state response from the unit step is equal to S. So S is the unit step response of the system. This S is the is called the step response. Okay, it is the response signal. It is the output signal when the input is the unit step signal. Of course, with zero initial conditions. Now, if we know L, if we know that the step response is the function S, then the problem is we want to find the impulse response. Now, from the impulse response is defined as the response when the input is delta, right? This is the very definition of the impulse response. It is the output. It is the response. It is the step. It is the zero state response from the system when the input is the impulse, unit impulse. Now we know the unit impulse is the derivative of the unit step with respect to time, right? So from differentiation property, we could take the d by dt out and take L in. So this is equal to d by dt L of ut. But from the problem, we know L of ut is S of t, right? So this is d by dt S of t. So here we have that the impulse response can be found by taking the first derivative of the step response with respect to time. The impulse response is equal to the derivative of the step response with respect to time. All right. Okay. Now the next property is called integration property. If we know that the convolution between x and h is y, then the convolution between, if we integrate x and put it into the system, the result will be the same as integrating the same integration on the output y. So using diagrams, we have we integrating the input, and then we put it into the system h, and we record the result. On the other hand, if we put it into the system first and then perform the integration, record the result again, okay, the result would be the same. Okay, in other words, again, if we denote L of x as h of t convolved with x of t, then from this property we know that if we take the integration of x of tau d tau going from minus infinity to t, the result will be the same as taking the integration of L of x of t, x of tau. We have to change it to x of tau and d tau. We could take the operator L inside the integration, right, without changing the outcome, just like the derivative. Okay. So, for example, if we know the impulse response from the system, we then can find the step response from the impulse response. In the last example, we found the impulse response from the step response. Now in this example, we're going to do reverse by finding the step response from the impulse response. The step response is the output from the integral of the input. Okay, and the actually is L du t, but u is integral of the unit impulse, right? And from that property, from the integration property, we know we can take L inside of the integral and get and get this. But L of delta is just the impulse response, right? So this is integral of the impulse response. So if we integrate the impulse response, the result will be the step response. Okay. Now the next property is called convolution identity. It means, it states that any function when convolved with the unit impulse, the outcome would be the same function. Just like when you multiply two numbers together, if you multiply any number with 1, you're gonna get that number back. So 1 is called the identity of multiplication. On the other hand, if you add any number with 0, you're gonna get that same number back. So 0 is called the addition identity of addition. Now same logic here. If we convolve any function with delta, we're gonna get that function back. So delta is called convolution identity. Okay. Right. Also, we note that if we convolve x with delta t minus tau, okay, the result would be x shifted by t0. Okay, this may come in very helpful in the future. Right? At any time, if you cannot catch up, or you would like me to explain a little bit more, or if I am going too fast, you can let me know. Right? You can let me know. And it's best that you speak up, because I usually don't look at the screen. If you raise your hands, I won't see it on the screen. So I think it's better that you speak up. I would be able to hear you. Now, block diagram representations. Suppose we want to simplify this system. Okay, let's take a look what this system does. We have the input x coming in, right? And the input x is applied to 3 things. The top one is the linear system H1. The second one is the linear system H2. And the third one, the bottom one, is the linear system H4. Now, whatever comes out of H1 and H2 are added together. Okay, and the result will be applied to another system H3. Okay, and the result from H3 will be added to the result from H4, and the outcome from the operation is y, denoted by y. Now we can simplify these two, okay, because we know from distributive property, if we add h of 1 and h of 2 together, if we add the results from h of 1 and h of 2 together, okay, whatever the result is, it would be the same as adding h of 1 and h of 2 together and apply h into it. So here, this would be x of t convolved with h1 plus h of t. Convolved with h of 2. Now from distributive, we could take x out, right? So x convolved with h of 1 plus h of 2. And so we have this. Okay, this is x of t convolved with h of 1 plus h of 2. So they're the same, right? So they're the same. They're the same. And then the result from here, the outcome here, is applied to another system h of 3. So we know from associative, right? Going from B to C, we use associativity. Okay, here in the upper one we have x of t convolved with h of 1 t plus h of 2 t, and then whatever it is, we convolve again with h of 3, right? And using associativity, we can do this: h of t convolved with h of 1 t plus h of 2 t, and convolved with h of 3 using associativity property. And this equation is exactly what we have here. So this is the system, right? We convolve x with this system and get the outcome back. So you see they are the same. So we could replace this whole ordeal with just one system, that is the convolution between the two impulse responses. And going from C to D, we use distributivity property again, and that is straightforward. So we get a D. So basically, in conclusion, we could simplify the whole thing here into this. Okay, the whole thing here could be simplified to get a D. Okay, so this is block diagram simplification. Okay, so now let's spend some time doing some examples. Determine let h of t equal to u of t and x of t equal to u of t minus u of t minus capital T. Okay, we want to determine y that is equal to h of t convolved with x of t. Now, let us get to know the signal x a little bit more. When you plot the signal x, okay, it will be u minus u of t minus t. So let's say that the time capital T is right here. Then the signal x would be going from 0 to 1 at time 0. And then it will remain at 1 until time t. Okay, and then it will go back. It falls back down to 0 after time t. So this is what x is. Okay, now we're gonna perform the convolution between h and x. So solution, okay, y is h convolved with x, right? And then from the problem, we could replace x with u of t minus u of t minus t. And then we could use the distributivity property and get h inside to get these two subtracted. Okay, now if you look more carefully, I'll be right back. Sorry, 1 minute. Now, if you look more carefully, you can see that these two are the same, except that the latter term, in the latter term, we delay u by capital T before we apply it to the system. Okay, so that reminds us of time shift property, the time shift property of a linear system. So if we denote the first term by f of t, then by the time shift property, we don't need to do this one again. We just simply shift f by capital T. So this is going to be f t minus capital T by the time shift property. You remember time shift property? Okay, time shift states that if f is the result from applying x into the linear time invariant system, then L of x t minus capital T will be f of t minus capital T. So this is the time shift property, right? And this is exactly that. Okay, this is L of u of t, right? And we denote it by f of t. And this is L of u of t minus capital T. So by the time shift property, this is equal to f of t minus capital T. Okay, so what remains for us to do is to do this, right? Now to do this, we plug in h as u. So, but h of t convolved with u of t is u of t convolved with u of t. Now we've done this several times, and we know that these two convolved, u of t convolved with itself, will result in t u of t, which is the unit ramp signal. So the latter term would simply be this expression where t is replaced by t minus capital T. Okay, so f of t is t u of t, and f of t minus capital T is t minus capital T u t minus capital T. Okay. Ooh, sorry. So we can simply plug these two into our equation. Therefore, the zero state response is t u of t minus t minus capital T u t minus capital T. Now let's simplify this even further. Okay, let's simplify this even further. by denoting, by drawing a real number. Okay, this is time, an axis, time axis, and then we have 0, we have capital T. These two instances were taken from these observations. Now, when time is less than 0, both of these are 0, right? So we have 0 and 0. 0 minus 0 is equal to 0. Now, from 0 to capital T, this term will be T, right? Because T is greater than 0 now, so U becomes 1. So this term will be T. But this term, though, because over this interval, the variable little t is still less than the capital T, right? So this parenthesis here is negative, and U as a result will become 0 over this interval. So over this interval we have T minus 0. Okay, so T minus 0, and the result is T. Now, when time T is greater than the big T here, this number will be positive, and so U will be 1. So the latter term will be T minus capital T, while the former term, the left term, will be T, because T is greater than 0. So this is T minus capital T, and it is T. Okay, it is capital T. Okay, so from here we have y, which is the outcome would be T when time is greater than 0 but less than capital T, and then capital T when time is greater than capital T, and 0 elsewhere. So if you plot this, the zero state response y from this rectangular signal, what you have is 0 here, and then climbing to T, and then stays at T forever, indefinitely. So this is T, this is T, this is 0. Okay, and this signal is a result from applying this signal to this system. Okay, so this is the zero state response. Now let's do one more. Let's do one more example. Okay, suppose we let h of t, a linear time invariant system with the impulse response equal to e to the minus t ut. Okay, and the input is the same signal. U of t minus u of t minus 2. Now let's make it a number. We want to find the zero state response, assuming all the initial conditions are 0. Okay, now the solution. The zero state response is equal to h of t convolved with h of x of t, right? Now we could plug in the functions given in the example. So we have e to the minus t ut convolved with u of t minus u of t minus 2. And then we could use the distributivity property to take the whole thing here inside the parentheses, just like we did in the last example. So we have e to the minus t u of t convolved with u of t. That's the first one. And the second one is e to the minus t u of t convolved with u of t minus 2. Now you see the pattern here. Okay, this term is exactly the same as this one, except that we are shifting the input 2 units to the right. Okay, we're shifting this 2 units to the right. So if our strategy is to find this one and denote it by, if we denote it by ft, then this term will be simply shifting f of t by the same 2 time units using the time shift property. Okay, so whatever left is to find f of t, but we know, we have done this several times, that e of minus t u of t convolved with u of t. We have done this many times so far, so I'm just gonna use the result that we have, right? So this is equal to 1 minus e to the minus t u of t. Okay, and so that means the function f is 1 minus e to the minus t ut, and f of t minus 2, simply replacing t here and t there with t minus 2. So this is equal to 1 minus e to the minus t minus 2 u of t minus 2. Okay, and the last step is to subtract them. Okay, plug in this to there and this to there. So the zero state response is 1 minus e to the minus t u of t minus 1 minus e to the minus t minus 2 u of t minus 2. Now we should simplify this just like we did in the last example, okay, by drawing the time axis and indicate the points of interest, which are 2. Okay, the first one is 0 and the second one is 2 here, taken from here. Now when t is less than 0, both of them would become 0, because of the unit step signal u. So we can say that 0 minus 0, and the result is 0. Now when t is greater than 0 but not greater than 2, the first u of the first term will become 1, while u of the second term will become 0, because t is still not greater than 2, so t minus 2 is less than 0, so it is 0, right? So here we have 1 minus e to the minus t minus 0, and the result is 1 minus e to the minus t. Okay, and when time is greater than 0, the first term will stay at 1 minus e to the minus t, because u is 1. The latter term, now u is 1 because t is greater than 2. When t is greater than 2, the inside parentheses will become positive, so u is 1. So we have this one. Okay, minus 1 minus e to the minus t minus 2. Okay, so we have e to the minus t, and then e to the second minus 1. You can check it, right? So using my calculator, e to the second minus 1 is equal to e to the second minus 1, 6.39, about 6.4 e to the minus t. Yeah. Okay, so in conclusion, the zero state response from the system will be 1 minus e to the minus t when time is greater than 0 but not greater than 2, and 6.3 about 6.4 e to the minus t when time is greater than 2, and then 0 otherwise. Now let's draw something. Let's draw the graph of y. Now when time is less than 0, y is 0, right? And when time is from 0 to 2, the signal is 1 minus e to the minus t, so it is slowly climbing up. Actually, it rises up quite rapidly, and the increasing rate slows down. And now at time 2, we simply plug in 1 minus e to the minus 2, and it is 0.86. Okay, now from time 2 on, we have this. Now let's check. If I plug into this, I'm gonna get 6.4 times e to the minus 2. I'm gonna get this number. Okay, so from time 2 on, the response slowly dies down. There. Okay, so this is the response from the system, right? Now let's do another example. Now suppose an LTI system has the property that if the input is u, okay, if the input is u, the output is e to the minus 2t ut. Okay, we want to find its impulse response. H of t. Now, solution. We want to find impulse response. The impulse response is the output when the input is delta. Okay, and we know that delta is the derivative of the unit step with respect to time. So delta is du by dt. And we know we can interchange L and differentiated derivative operator, so we interchange them. But then L view is given as e to the minus tut, right? So we have d by dt e to the minus 2t ut. Now let's do this derivative. I hope you still remember how to do it. Now d by dt e to the minus 2t ut. Now there are two parts in this differentiation. The first part is e to the minus 2t, and the second part is ut. Okay, so we think, when we see this, we think of product rule of the differentiation, right? So this is equal to e to the minus 2t du by dt from product rule plus u of t d by dt e to the minus 2t. This is product rule of differentiation. Now, what do we know about du by dt? This is delta. Okay, and this is minus 1/2 e to the minus 2t. So we have e to the minus 2t delta t minus 1/2 e to the minus 2t ut. But as we know that delta is valid only when t is equal to 0, but then when t is equal to 0, this is going to be 1, right? So we can simply replace the first term with 1. So we have delta t minus 0.5 e to the minus 2t ut. So there we have, with the impulse response from this system, it's given by this expression. So therefore, the impulse response is delta t minus 0.5 e to the minus 2t u of t. That's the answer. Okay. All right. Any question, guys? Are you still here? How many people are there? 1, 2, 3, 4, 5, 6 people out of 31. That's impressive. Now the last issue that we need to address is called properties of LTI systems. If you remember from the last chapter, we talked about properties of systems, where we had linearity, time invariance, memoryless, invertible, as well as bistable. Okay, but now if we restrict the systems to be LTI, if we focus only on linear time invariant systems, then these properties will be very easy to determine. So I should point out that we focus only on LTI systems. So in other words, when the systems are linear time invariant, then deciding whether the system is memoryless or invertible or causal or stable is easy. Okay, an LTI system with the impulse response h is memoryless if and only if h is a constant multiplied by the unit impulse. Okay, for example, if if h is e to the minus tut, then system is not memoryless, because it is not in this form. Okay, but if h of t is 3 delta t, then it is memoryless. It has to be something, it has to be some number multiplied by the unit impulse. Okay, now invertible system, LTI system with impulse response h of t is invertible if and only if you can find another function, okay, that if we do convolution between h and that function, you're gonna get delta back. Okay, now to find that function is not easy. Okay, for example, if h of t is equal to delta t minus 4, okay, then since delta t minus 4 convolved with delta t plus 4 is equal to delta t, we know that from shifting property and identity, right? It follows that the inverse system h of h prime is delta t plus 4, and this system is invertible. Now if you look at this, it makes sense, because what this system does is simply shifting the input to the right, is simply delaying the input 4 time units, right? So the inverse system will simply be advancing the input by 4 time units, so that if we cascade them, if we put them back to back, you're gonna get the signal h back, signal x back. So in other words, if you do this, if you apply x to this system, and then apply the result to h prime, you'd have x back. Now if you can find this, then h will be invertible. But if you cannot find this, then h would not be invertible. Now in this particular example, h is delta t minus 4, so h prime would be delta t plus 4, so that this is delayed, this is advanced, right? If you delay it by 4, you have to advance it by 4 to compensate for the delay, so that to get the original signal back. So this is what it does in this example. Now causal. An LTI system with the impulse response h is causal if only if the impulse response is 0 when time is negative. So if you plot the impulse response, okay, and you notice that the impulse response is 0, okay, is 0 here, it has to be 0. Now you don't care about the positive time as long as the negative time results in 0 impulse response, the system will be causal. Okay, to determine whether the system is causal or not, just look at the negative time. During the negative time, h has to be 0 for the system to be causal. Alright, you don't care, just ignore the positive time. Positive time can be whatever. Okay, we focus only on the negative time to determine causality of a system. For example, the system h is equal to the impulse response of the system is equal to e to the minus tut. Now, because of the function u, right? Because of the function u, we know that h is 0 when time is negative. So h is 0 when time is negative. So this system is causal. On the other hand, if h of t is e is t u t plus 2, then you see that h of minus 1 is minus 1 times u of 1, and it is minus 1, right? Which is not 0. So this system is not causal. For it to be causal, whatever you have negative time here, h has to be 0 for it to be causal. But now there is at least one negative time for which the impulse response is not 0. So this particular system is not causal. Okay. Now the last one is Biot stability. To determine if the system is bounded input, bounded output. Biot, if you remember, stands for bounded input and bounded output. To determine whether an LTI system is Biot stable is easy. You perform this integration and see if the result is finite or not. If the result from this integral is finite, then the LTI system will be Biot stable. But if the result from this integral is not finite, then the such LTI system will not be stable. Okay, so easy. Look at the integral. Remember, be sure to put the absolute sign around h first. Okay, if it is finite, then it is Biot stable. But if it's not finite, if it is infinity or minus infinity, well, minus infinity is not possible because we have put the absolute signs around h, so it has to be just infinity, then it is not Biot stable. So determination of Biot stability is very easy. If you are able to do the integral, then you should be able to determine the stability of a system. Now let's take an example. The system, an LTI system, has this impulse response. We want to find out whether it is stability. So to find out whether it is stable or not, we have to do this integral, right? Now h is an exponential and it is always positive, so we can drop the absolute signs and put 3e to the minus 5t ut dt minus infinity to infinity. But because of the effect of u, okay, when t is negative, the whole thing will be 0. So we simply have to replace the lower boundary with 0 because of u, right? So we have integration from 0 to infinity, and over this interval u is 1, so we can drop u. So we have 3e to the minus 5 t dt. Now we can integrate it as usual. Minus 3 over 5 e to the minus 5t minus 1, where t goes from 0 to infinity, and that would be that'd be 3 over 5, which is obviously not finite. Which is obviously finite, so we can conclude that the system is stable. Now, another one where the negative sign here is dropped. So, this integration is going to be minus 3 over 5 e to the minus 5t minus 1. I'm sorry, e to the 5t minus 1. Okay, where t goes from 0 to infinity. So in this integral, I have e to the infinity, right? And that is minus, I'm sorry, this is 3 over 5. 3 over 5. And that is infinity. So this system is not stable, because this integral is not finite. Now what about ht equal to ut? Again, check the stability. Absolute u, we can drop the absolute sign, right? And start the low boundary from 0. Okay, so that is infinity. So this system is not stable. Now, for this one, okay, t e to the minus t ut, right? This is equal to integration from 0 to infinity t e to the minus t dt. Now why is this? Because if you have to start from 0 on, and because this, when we start from 0, this term will always be positive, so I could drop the absolute signs. So I have this. Now to evaluate this integral, I have a trick for you. Okay, so we know that integral from 0 to infinity e to the minus t dt. Okay, you should check this out. This is equal to 1. Actually, t e to the minus alpha t dt. If you check it out, you know that it is equal to 1 over gamma, alpha, sorry. So if you differentiate it with respect to gamma, I'm gonna have integration from 0 to infinity. I'm sorry, this is t e to the minus alpha t dt will be equal to 1 over alpha square. So, but here in this case, alpha is 1, right? So using this result on this integral, I have equal to 1, which is obviously finite. Okay, so this system is stable. Okay, now let's look at the last example for today. We want to find the stability of the following integrator. Now, integrator is linear time invariant. And you can prove that quite easily. So I'm just gonna omit the proof to show, well, actually to show it. To show, I have to show that it is both linear and time invariant. Now to show linearity, okay, L of AX1 plus BX2, I have to show that it is actually, we can take L inside, right? So this is integral going from minus infinity to t, ax1t plus bx2t dt, right? And we can take the integration sign operator inside. So we have a integration from minus infinity to t, x1, actually I have to replace it with tau. Tau d tau, x1 tau d tau, okay, plus b integration x2 tau d tau. But this, from our definition, is just y1, okay, and the other term here is y2. But actually not y1, it is L x1 plus b L x2. So from this last step we know that the system is linear. Now to show that it is time invariant, okay, L of x of t minus t0 is equal to integral minus infinity to t minus t0 x of tau d of tau. Actually, sorry, it has to be t x of tau minus t0 d tau. Now I can change a variable, okay, I have minus infinity x of tau d tau. Now this has to be t minus t0. Now this is from change of variable in calculus, and this is L of x of t, replacing t with t minus t0. So from this last step we know the system is time invariant. So now we know that this system, this integrator, is both linear time invariant. We could just check the stability only looking at the impulse response. Now we know that an integrator is LTI. So next we find the impulse response. Okay, now from definition, impulse response is the response where the input is the unit impulse. So we can simply plug in the input here, integration here, with on the unit impulse, right? And that is integral from minus infinity to t delta tau d tau. And we know that this integral is u of t. Okay, but we know from this example that when h is ut, the system is not Bible stable, but h of t dt is from 0 to infinity dt, which is not finite. So an integrator is not Bible stable. Okay, because of this. Because of this. All right. So that's it. Now we are at the end of chapter 2. On Tuesday in class, we will start chapter 3, which is Laplace transforms. And I think the midterm should end here. But then, if the term ends here, we don't have enough time to cover enough Laplace transforms for it to appear in the midterm. So I'm gonna have to make some adjustment to how we do the examinations. We're gonna need another short examination coming up after the midterm, and that short examination will cover Laplace transforms and Fourier series. So instead of 2 examinations, I think we need to have another one and make it 3 examinations. In the midterm, which is the first examination, will be about chapters 1 and 2. The short examination, which is in the middle, in between the midterm and the final, will be about the Laplace transforms and the Fourier series. And the final exam will be about Fourier transforms, sampling theorem, discrete time signals and systems, and Z transforms. I think that is best for you guys by breaking up the 2 exams into 3, so that we don't put too much stress on the midterm. Okay, I don't want to try to hurry up and finish the Laplace transforms over just 2 lectures. That would be too fast. Okay, how's that sound? Is that okay? Is that okay for you guys? Are you still there?
Okay, I'm still.
Okay, so I'm gonna lay out the details on Tuesday, right? But that is what I'm thinking about. Just want to share it with you guys. And so we have to end today. And thank you very much for coming in, and thank you for your attention. And I'm gonna upload this clip as well as the lecture notes on Google Classroom. Please be sure to check it out. Okay, so until Tuesday. So let's see you again on Tuesday in class. Bye bye. Yeah, if you have questions, please feel free to ask now.
Excuse me?
Yes.
In the midterm, does not have Laplace?
No, midterm there will be no Laplace transforms in the midterm, because we only have 2 lectures left, right? And 2 lectures is not enough to cover the whole Laplace transform. So we need another short exam. Okay, we need another short exam, and Laplace transform.
Midterm?
Yes, after midterm. How's that sound? Is it okay?
Okay.
All right. I'll write out the details for you on Tuesday. Don't worry. Okay. Any other questions? Okay. So see you on Tuesday. Bye bye.
Thank you, teacher. See you.
Okay. Bye bye.